Hello everyone, welcome to this tutorial. My name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to get rid of speckle impact without losing a spatial resolution in the radar data. So if you watched the previous video on my YouTube channel, definitely you know about this paper comparing Sentinel-1 and 2 indices for agriculture land use monitoring. In that tutorial, I showed you how to calculate RVI index that's highly useful for the vegetation cover detection using radar data. We utilized the equation number 3 using Sentinel-1 data to highlight the vegetation cover, and this is the results. I will show you how to do these calculations and everything. Don't worry. In the first step, I'm going to show you what I'm going to do in this tutorial. After RVI calculated, the brighter area shows higher vegetations and lower area and lower actually or on the other hand, the brighter area shows higher vegetation cover and darker area lower vegetation covers, and you can see. But it's highly affected by speckle filters. And now you can see the corrected image. This is the de-speckled image in which speckle impact highly smoothed in the final output. These are for the same date and same results, but you can see the different quality. And also I'm going to show you how to use a multi-temporal de-speckle processing to reduce the speckle impact without losing spatial resolution. It is a very important thing. If you are a radar user, definitely you know that whenever you use a low-pass filtering technique, highly reduces the spatial resolution. But now in this tutorial, thanks to Google Earth Engine capabilities, I'm going to show you a kind of time series analysis that allows you to reduce the speckle impact and keep the spatial resolution almost same. So now please follow this tutorial to see how we can do this process in the Earth Engine. First of all, make a new code editor environment in the JavaScript. In this tutorial, I'm going to use the JavaScript language. It is very useful in Earth Engine for the time series analysis and image processing. So, and also if you are a Python user, don't worry, there are a lot of Python tutorials on my YouTube channel and you can find it there. So, how to do this tutorial and also how to get rid of speckle impact in the radar data and keeping a spatial resolution almost same during the time. This is the target question in this tutorial. To address this question, first of all, select your region of interest. And this tutorial can be used for all around the world. I'm selecting a very small region from my own country, but you are free to select everywhere in all around the world. So now in Iran, actually, it's my own country here. In the southwest of Iran, we have a lot of agricultural area and agricultural fields, and I'm gonna select a part of that, but you can select your own region of interest. The only thing is matter, you must select a agricultural area, no matter it is in Iran or any other countries in the world. And Sentinel-1 data hopefully is available, publicly available for all around the world, and definitely you will have no problem to do this tutorial for your own region of interest. So let's select your region of interest using drawing tools available here. I'm going to use rectangle here and draw a part of region of interest and also select the region of interest first. So to have focus on the study area, when the code is running, map.center object allows you to have a focus on using map.center object geometry, just like that. For example, when I run a code, we will have a focus on a study area. Imagine that if we are in this situation and when you run the code, jump to your region of interest immediately. So if you want to have satellite background here, you can use map.set options here. Map.set options, you can change the background view to the satellite, just like that. Run a code, and now easily you can see the code runs based on a satellite view background. So that helps you to actually discriminate the vegetated area, farmlands, water bodies, and bare lands, etc. So in the next step, we need to call Sentinel-1 data. So make a new variable as Sentinel1 equals to, go to search places on dataset and look into Sentinel-1 data. As you can see, Sentinel-1 GRD ground range detected data is available here. If you click on the data, you can see the data characteristic and properties. And here, meaning that shows the data is available since 2014, and you can get extra information about the data, band combination, and etc. Let's import it into the code, and here I have it as an image collection in the upper tab here. So assign the image collection to the Sentinel-1, just like that. And now you must filter your data based on time span and also the region of interest. Filter date. For example, I'm gonna calculate the RVI index. First, I'm gonna show you how to calculate the RVI index because maybe you cannot find the previous tutorial, and also now I'm gonna show you how to do these calculations and how to get rid of Speckle impact. Just if you want to know more detailed about RVI index and how it works and etc., feel free to check the previous video on my YouTube channel. So get filter date 2003 and 2004. I'm gonna use 2023 data for the region of interest. Then filter bound to bound your data to the region of interest or geometry, just like that. So let's get a print from Sentinel-1 data to see how many images available for this period of time. So let's run a code here, and as you can see, 87 elements available for this year. Drop down the menu, and here you can see each image with the existing bands and the properties. The properties here refers to the metadata information that we have for the data and allows us to make different filters based on image characteristics. For example, here one thing is important is about transmitter-receiver polarization. It is important to have transmitter-receiver polarization as VV and VH together. So in the first step, make a new filter as least contain, Earth engine.filter that least contains. So here just copy transmitter-receiver polarization just like that and paste the parameter here. It is VV. VV stands for vertical. As you know, in the microwave region, the direction of electromagnetic radiation is very important, vertically and vertically. For example, the microwave wavelengths or the microwave waves sends vertically and received vertically again by the instruments, and sometimes it is VH. What does it mean? Vertically sent and horizontally received. So VH. Most of Sentinel-1 data available in VV and VH. HH and HV is not available, at least I haven't seen for the regions I was working. So I have no information about that polarization in the Sentinel-1 data. So back to the code here. This is the first filter that we have to use them for the Sentinel-1 data. The next parameter is about instrument mode. Remember that the instrument mode should be equals to IW. So another filter or equal filter, Earth engine.filter.equal. So I'm gonna use images in which instrument mode equals to, because I'm using equal filter, equal to IW, instrument mode, or you can copy and paste it to avoid any syntax error. It must be equal to IW. So if you run a code, same number of images returned. For some of the regions, when you use these filters, the number of returned images will change. That's why it is necessary to use this parameter for all around the world. Sometimes the number of images changed and sometimes not. So the other parameter is about actually here the orbit properties pass. So the orbit properties pass could be ascending or descending. So and the ascending and descending mode actually is a kind of orbit style that affect on actually the geometry of images. And when the geometry of image and geometry of imagery changes in the radar data, actually you can see the anomalies and different backscatter values. That's why we should use the same orbit properties pass in the data. You can choose the ascending mode or descending mode. So here you can select, or you can make another equal filter, Earth engine that filter equal. So the orbit properties pass, copy and paste it here, could be ascending mode or descending mode. Let's try with ascending mode to see which one of them is dominant for this region of interest. My suggestion is that try with ascending and descending mode and see how many images are available. If anyone, for example, ascending or descending was higher value and also higher number of provides higher number of images, then you can go for ascending and descending. So run the code. We had 80, I think more than 80 elements, but here we have 61 elements, meaning that 61 from 80 images belongs to the ascending mode. In that case, I prefer to use ascending mode because more number of images available in this case. So all necessary filters settled, and in the next step we are ready to calculate the RVI. What should I do? So make a new variable here. The RVI stands for radar vegetation index, equals to get Sentinel-1 data first, and then define a loop structure using .map. Make a function inside the map structure to do a calculation and return a result. So the input image, each Sentinel-1 input data in the code actually called as img here, or you can pick any other name you prefer. So now in the body of function, you can write the step of processing. First of all, I'm gonna filter the target bands here. As you can see in the equation for Sentinel-1 data, we have VH and VV, the polarizations available. So if you go to the bands here, you will find three: VV, VH, and angle. But we don't need the angle. This is the incidence angle for each data. Get rid of the angle first and select the VV and VH. From each input data IMG, I'm gonna select the VV and VH, just like that. VV and VH, both of them selected. So in the next step, if you read the article, you will know that we have to use the sigma naught parameter. Sigma naught is a backscatter unit of conversion, backscatter unit of measurement for the radar data. But if you go to the data properties here, you will find that the GRD data available in decibel format. And now I have to convert the decibel data to the sigma naught values. So it's very simple. There is an equation allows you to do conversion between decibel and sigma naught here. So the sigma or backscatter measurements equals to get the bands first, the target bands selected, or before we must make an image, Earth engine.image, including value 10 and square 2, and here get the images VV and VH in each date and divide them into 10. So this is an equation allows you to do conversion from decibel format to the sigma naught. So there it is. And in the next step, now we can calculate the target index. The target index equals to get the sigma naught image and write the expression using expression function. So double quotation and in a string format, as you can see, we have a division here, a numerator and denominator. In the numerator, 4 multiplied to VH. separate numerator and denominator with two parentheses and division sign. So in the numerator, for multiply to VH. So in the denominator, VH plus 2VV, just like that. So now we have some unknown parameters. VH and VV are unknown for the code. So let's define them. First unknown, VH, equals to, from sigma select the VV band. Now we are defining a noun variable for the unknown. So, and the 4 is also known for the code because this is a number. So the next is, VH equals to VH, and VV equals to, from sigma get the VV image. So the RVI calculated, return the band name to the RVI. The function finally return a result. The result here is the index, as you can see. So once the index calculated, we need to have some of the properties. As you can see, there are a large number. We have a big list of properties available here, but none of them gonna be used in the next step because we already filtered our data based on the most important one. The only important properties for the next step are system time start and system time end, because we want to do time series analysis and it is very important to have these two parameters for the next step. So let's copy properties. I'm gonna copy properties from input images only system time start, system time start, and system time end, just like that. System time start and system time end selected here. Let's get a print to see how many RVI data is available. 61 RVI calculated and returned. Drop down the list here and you can see we have a band as RVI, we already named, and also there are 3 properties. One of them system index, the ID of each image, and system time start and system time end. So the RVI is calculated, and now actually we want to do the Speckle process here. Start a new time series analysis here that allows us to actually get rid of the RVI values. So to get rid of the Speckle impact in the RVI image. Actually, the RVI is like this now, and I will show you how to do the visualization. No worries, just I want to actually do a step-by-step processing to give you understanding about the Speckle process. And RVI is like this now, and also as you can see, the brighter areas shows higher vegetation covers and vice versa. So, but as you can see, it's highly impacted by speckles or salt and pepper effects, and now I'm gonna actually reduce the impact of speckles while keeping a spatial resolution same. So now actually I'm gonna use a moving average technique here. In the moving average technique, we must define a window, a temporal window. For example, for 1 month, I make a temporal window for 1 month and then try to calculate the average of RVI images for each month, but here I'm keeping the temporal resolution same. And also in the temporal analysis, in the multi-temporal analysis here, we don't lose the temporal frequency. The temporal frequency is same, but the values in each image actually retrieved from the temporal window analysis. I will show you how it works. So, for example, if we have 61 elements, finally we will have 61 elements, but their values retrieved, the new values retrieved from a temporal window, a dynamic window that changing every 30 days, that allows us to keep the same frequency and also with a better quality. So I will show you how it works. Don't worry, just try to have a focus on this tutorial and try to write the codes. And if you face any problems in the code, no worries. The code link is available on the below this video on my YouTube channel, and you can reach me out there and find the code and copy mine with yours. And still, if you had any problem, feel free to reach me out and put your comments on the channel. So the RBI calculated, and now I'm gonna actually show you how to define a dynamic filter for the multi-temporal analysis. First, let's define the number of days we want to have filter based on. For example, I will define 15 days after and 15 days before each image selected in this scenario. This is the window size or day. So now the window size should be converted to the millisecond format. The millisecond format is EarthEngine.number. First of all, we should convert the day to the millisecond format. .number date, we consider the date as a number and convert it to the millisecond by a constant, by an equation and constant values. 1000 multiply 24 multiply 3600, as you can see here, 3600. So now 15 days equals to this millisecond value, or you can print and see how millisecond value works. Why millisecond? Why we don't use actually the day, same as what we have? We have to convert the date information to the millisecond because that's how the Google Earth Engine works, and that's how the Google Earth Engine uses to explain the time and temporal characteristic. So back to the code here. So actually the window size defined based on a millisecond, and now I need to define a filter that allow me to look into 15 days after and before. So here a new filter created, EarthEngine.filter, that maximum difference. I'm gonna look into the maximum difference 15 days after and before in each image. Actually, the window size, the maximum size of window defined by the maximum difference here. So a couple of arguments should be considered here. The first one is the difference. So here actually the filter is the window size that is creating based on millisecond and day. So the difference already defined by mils. And also and this filter, for the filter we need to introduce the property in which a millisecond actually can work. So millisecond based on what? Based on time, or based on location? Based on what? Based on system time start, the key property already introduced here. So the left field, as I'm gonna have two kind of collection here, two kind of field from the first collection and second collection, left field and right field should be introduced here. The left field equals to system time start, because I'm gonna actually extract from existing data collection. I'm gonna find the images 15 days after and 15 days before of each images. So that's why I will have two collections, and these two collections must have a same property, that is system time start, that explains the maximum difference by millisecond. So it's a little bit tricky if you're first time using this code and knowing about this code, but it's too easy. Just try to practice. And if you are a remote sensing expert, if you want to learn remote sensing smoothly, and it is important to have enough practice in the remote sensing. Satellite data analysis is very important, and it is highly technical, and also you must try to develop your skills in the scripting method. Hopefully in the Google Earth Engine we have a structure. It's not designed for the programmers, it's designed for the researchers and scientists, and also for everyone who want to work with geospatial data. So it is very important to know how to use the functions and to how combine or integrate functions together to reach your final results. So I'm trying to explain these steps that give you insight about how to combine these functions together and get the final results. If you follow all tutorials and try to learn and learn and learn, that's definitely finally you will understand the integration process between different functions and making batch codes for your own purpose. So maybe only one tutorial and watching one time is not enough. You must try so hard and try to increase your knowledge in the Earth engine and also in the remote sensing data analysis. So back to the code. The filter also defined here. Now I need actually to use the filter to search in the RVI images, existing images, and select images in which 15 days after and before each data. The filter is created, but now we must define a function to allow us to do this looking process. Join Earth engine join.saveAll. So the save all is a joining process that actually allow us to look into the data based on the temporal window created. So now we must actually combine the join and filter and also the RVI images in the same structure. So the join collection equals to first define an image collection structure just like that and bring the and also call the join function first. Through the join, I'm gonna actually find all images in 15 days actually distance for each data from RVI to RVI. Both of them should be same because I'm gonna find the images with 15 days difference or 1 month difference in time after and before each image existing after and before of each data available in the dataset. So I will show you how it works, and then condition will be filter. As you can see here, the temporal window called, image called, and join called, all of them integrating in the same structure, and I'm showing you how to use the join.apply for the looking into the target data. So let's print the join collection to see how it works. Join collection and run a code. In the right panel, as you can see here, drop down the feature list, and here you will have RVI still, same number of images returned, but here we have one new property as an image that included actually all images in 1 month distance compared to the original data. So these are the images 15 days before the target data and 15 days the after. As the temporal frequency is temporal frequency is weekly, I think, the Sentinel-1 data, that's normal, these number of images. And also the save all also save the RVI image for the current date, and also the before image and after image also listed. That's why we will have 5 number of images here. So in the next step, I'm gonna show you how to calculate the average of 1 month's data and replace it instead of the RVI. In that case, we will have same number of images, same frequency, but the values in each pixel comes from the averaging from images available in 15 days after and before. So now let's make a new function inside the loop structure, because for each image I'm gonna have a function to select these 5 data for each date and then return the average. Each input image as img called here. So now images equals to, as you can see, we have a property as our image here that included couple of images. Earth engine that image collection, I'm gonna convert them to an image collection from images available from img.get, as this is These are the bands but available under property, so we can get them using .get, not select. If they are banned, you can use the RVI or you can use the select. But as they are in the properties or under properties structure, .get should be used here. .image, just like that, and get the average using .mean. So you can use any other statistical parameter, but for this application, this type of data, the average method is much better than the others. That's why we say moving average, because we want to get the average image for a temporal dynamic window that varies through the list of data we have. So the function returns the original image add bands with the actually moving average or moving average result or despeckled result. You can return its name, change the name to the, for example, the corrected. That's better. The corrected image with the properties from input data, system time start and system time end, just like that. So let's get a print to see what we have in the joint collection. In the right panel, again 61 elements returned. Spatial resolution is same. The temporal frequency is same, sorry. For each date, RVI and corrected is available. The corrected actually calculated from moving average dynamic window we already created. So now I can show you the quality of output between these two data. We did the moving average process and the speckle process, and now I'm gonna show you how the quality of results. Map.add layer is a popular function, allows you to do this process. So for the visualization, join collection. First select the original data RVI, put them in a stack layer using .to bands and clip the output based on geometry. Just like that, leave the visualization parameter empty. The RVI is the name of the layer and use the false to avoid automatic visualization. Another add layer, this time for join collection .select, this time for corrected data, put them into a single layer stack .to bands and clip the geometry just like that. The corrected version and use the false at the end. Let's save the code and run it again. After a few moments, you will have two new layers, RVI and corrected data. Let's select a date randomly and then compare it between after and before correction. So for example, this image is for April 16. Selected, increase the contrast by 90% of value and click on apply. April 16. This is the original RVI value for this date. So go to the corrected version and let's select a date in which vegetation cover is maximum, because that is better for the agricultural studies, because this paper also talking about growing season or something like that. For example, let's go to the August, for example, August 7, 2023. Let's increase the contrast by 90% of values available in this image. Yes, this is better, in which vegetation cover is higher. And August 7 in the corrected image, August 7, August, year, June, July, August. There it is. And increase the contrast. Click on apply and close. This is the corrected image. As you can see, the spatial resolution is same, but only the speckle impact reduced. The quality of output for the interpretation and getting the final result is perfect, as you can see. And now you can see the differences between fields clearly. So now in this tutorial you learned how to do the Speckle process using multi-temporal data analysis instead of low-pass filtering technique that highly actually affect on the quality of output, specifically in the spatial resolution. So I hope you enjoyed this tutorial. Let's try to write this code and compare your code with mine. And if you had any problem or question about this tutorial, feel free to reach me out on my YouTube channel, and then I will try to answer your questions as soon as possible. Please share this tutorial with other remote sensing, with other experts who are working on remote sensing community, and I will be happy to share more and more tutorial with all of the users in global. Thank you.